Hi everybody, welcome back into the dungeon, and today something a bit different. No repairing, just a discussion on the functions of a VTVM, how it works, what it does, and hopefully that'll kind of help you especially if you're starting out, or if you've got I'm hoping that you do have a sort of a rudimentary understanding of electronic circuits, and then this will sort of help you to get on your way with regards to VTVMs, how they work, what they do, what they don't do, and so on. And a lot of guys are now buying up these old VTVMs and restoring them, which is great because they're wonderful. A lot of advantages to them. So enjoy the ride with me as we dig into this VTVM circuit. And as you look at the schematic over here, the name is out of the page. I've got to be really careful where I draw up here. It's this schematic is the Kyoritsu K142 Japanese VTVM, but actually it's pretty much identical to a Heathkit. This is a Heathkit over here, an IM11. This is an American made, or an American version of the Heathkit IM11. It's just called an IM11. In Germany they came out as an IM11D, and if you look on the schematic behind me over here, then you will see there's a little blue resistor over there somewhere, and that blue resistor is found in the American version, but it's not found in the German version. I'll come back to that later on. Let's just get a look at the functions first of all of this multimeter, of this VTVM. So if we go to the VTVM front panel, we see it has a range selector. That's not a range selector, sorry, that is a function selector, and on the right side we have a range selector. It has 4 basic functions. It can measure AC. It actually only has 3 basic functions. It can measure DC voltages, either a positive or negative polarity, and it has an ohms scale, so you can measure resistance as well. And then your range selector will allow you to select different ranges for the voltage running between 1.5 and 1500, and for resistance from 1 ohm to 1 mega ohm. So it's got quite a broad range. The other thing you find on the input is a zero adjust, and that is to set the meter at 0 with no input. We have an ohms adjust, which is to set the meter at the needle at the infinity mark, with no resistance load connected during the ohms measurement. And then we also have an AC balance pot. Now some meters the AC balance pot is in the back, some it's in the front. Just depends on the make. Other thing you can see on this one over here, sorry I'm having to lean over, is you have a separate DC input compared to the AC and ohms input. Now on this meter it only has a single input, where AC, DC and ohms is all measured at the same point. We'll see that in a minute as well. Let's go back to the schematic, and we want to start with the meter driver circuit. So the meter driver consists of a single 12AU7 tube. A 12AU7 tube is a dual triode tube, so it has 2 amplifying triodes inside of one envelope. If we have 0 input, then of course we want our meter to indicate 0. And in order to do that, we have to present a voltage across the meter that has no potential difference. So there's no voltage difference across the meter, and then the spring drives the meter needle to rest at 0. Alright. This 12AU7 is connected in what is known as a long-tailed pair to be a differential amplifier. Now what does that mean? Let's have a look. First of all, we're going to have a positive voltage sitting on the 2 plates or anodes. So that's going to be at around about 90 volts, plus 90 volts, more or less. Then the two grids, or what do they call them in English? I can't remember. I speak American these days as far as tubes are concerned. Anyway, the two grids, they are held at 0 volts through a very high impedance resistor. You can see on the right hand side from pin 7 we've got a 10 mega ohm resistor taking it to ground, and over here on the input of the drive we have a 3.3 mega ohm, and it's normally going to be switched either through this network of resistors for AC and DC volts, or through this network of resistors for ohms. So it's also going to have a very high input impedance going to ground, effectively holding the meter at ground when no other input is present. So with both of these triodes grids at ground, we can now bias the cathodes, and the cathodes need to be negatively biased compared to the grids. And how do we do that? We have a 130 volt transformer getting rectified through a diode and smoothed through a 20 microfarad capacitor. Please replace this capacitor. If it's the old original capacitor, it's too old, it starts to get leaky, and you're going to get messy measurements, and you won't be able to set up your AC balance correctly. There's all sorts of problems that arise, so please replace it. I know that these old meters, they've got those beautiful old paper capacitors in there. They look great, they work like crap after too long. Replace the thing, or restuff it if you want that look. Okay, rant off. Let's continue. 130 volts. So I said there's 90 volts over there, so that means that down here, this point over here is going to, if that's 90 volts over there, there's got to be about minus 30 volts over here. And that's actually what happens. So I've got 130 volts, 90 minus 40 volts over there. Any case, let's have a look at that. If I've got 130 volts sitting between these 2 points over here, I'm going to just zero everything again. So I've got 130 volts sitting across there, and I've got 22 kilo ohms here, and I've got two 10k resistors over here. So at this point is going to be almost halfway, and that halfway point is going to be connected to ground through a 100 ohm resistor. So we have a virtual ground sitting there, and a real ground over here, which means I'm going to have negative 40 volts here and plus 90 here, more or less. This negative 40 volts will sit on this rail over here. It'll pass through a 220k resistor on the left side, going up to the cathode of the first triode, and then through a 270k resistor going to the cathode of the second triode. And you're going to say to me, Derek, why would they not use the two of the same value of resistors over here? Let's have a look what happens. I've got a negative bias over here, and when I get a negative bias of my cathode compared to my grid is now positively biased, and I'm going to have a current flow from cathode to anode, and I'm going to have a similar current flow through this side. If these two resistors were exactly the same, what would happen is, because this valve or this tube, these two triodes are not perfect, we're going to have a slight difference in the amount of current flowing through there. It's just the way things are. And also these two resistors might not be perfectly the same, but they're going to be close. And here's where we can run into problems, because if one begins to conduct just a little bit more current than the other, then the other one will start to and this is part of the meter drive principle, so it's good that I'm showing this to you. So as I start to conduct current through my 220k, let's say they were both 220k just for this purpose, then theoretically we should see the same voltage. So V1 and V2, voltage 1 and voltage 2 should be exactly the same, and then switched through this meter we're going to get a zero potential over here, and the meter will be at rest. But because the triode might be a little bit different between the one half and the other half, we're going to start to see an increased current flow through one of the resistors, and V1 can increase. When V1 increases, V2 can decrease. But what's going to happen is as V1 starts to increase, this voltage starts to reduce between the cathode and the grid, and it'll stop conducting and it'll start to go down again, and this one will start to increase, and we can have oscillations happening if we use two of the same value of resistor in the biasing circuit. But at the same time, we do want, for a meter at rest, we do want the voltages over here to be the same when the meter is at rest, when there's no input. So how do we achieve this? We use two dissimilar resistances, which means that in order to set up V1 to be the same as V2, I have to pass a different amount of current through these two resistors. And by allowing a different amount of current to pass across these two triodes, I can avoid an instability and avoid oscillations. The problem being that, of course, at this point in time now, I am going to see different voltages over here. So what the engineers then did is they installed this 10k resistor over here with a 100k resistor going across to my minus 40 volts, and I will balance out the voltages through these resistors while still maintaining a different amount of current through there, so that voltage 1 will be equal to voltage 2 when there's zero input, even though the two current flows through the two different triodes are different, and that way I don't have any oscillations and my differential amplifier is stable. Big explanation, but I've been puzzling over that for a while the answer was quite obvious. Okay, so now with zero input and these two conducting, let's say these two conducting and these two voltages sitting at this point being exactly the same, I have zero current flow through the meter, through the dial over here, and then it's at rest like you see right now over here. Now when I take an input voltage, I will upset the balance of voltages at this point, because now this portion of the the triode will conduct more than this portion. This voltage will begin to increase, that voltage will begin to decrease, and it will actually amplify the difference between these two circuits. I'll get an increased voltage sitting over here, I'm getting a lower voltage over there, and now I'll start to pass current through my needle or through my meter, and my needle will rise according to the amount of voltage presented at the input. That is the way this meter circuit works. As a result, all of the functions, whether it's AC, ohms or DC, they all need to be turned into a DC voltage at the input of my triode. Let's start with DC voltage, because that's the easiest to explain for now. So, on my DC voltage input, I get DC volts coming through and sitting on this chain of resistors over here. And if we add these up, that's 7, that's 9, that's 9.7, 9.9, 9.97, 9.99, 10 mega ohms. There's a 10 mega ohm resistive chain going to ground over here. If my input was, let's say, 1.5 volts DC, my meter selector will bypass this resistor chain. My input DC will still see this 10 mega ohm load, but the voltage will pass directly through the function switch, and I will get my 1.5 volts coming to the input over there, and at 1.5 volts on my lowest scale setting, which is 1.5 volts, I will get a full scale needle deflection on the meter. That's all very well and good, but what if I bring in 150 volts? If I had to leave this switch in that position, when my DC now again passes through here and it comes down there, bang, 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 bang through there, and I bang it with 150 volts over here, well, that poor needle is going to go to the end of the scale and try and climb off the other end. Not good for the meter and not useful to you. And this is where our voltage resistors are now in use. So if I'm putting in 150 volts DC, then it's going to come, let me just pass it through here again, it's going to come through there, through there, through there, down here, and of course that voltage, as we would know, hopefully you know it, that when you pass a voltage across a series of resistors, the voltage will drop according to the resistance that it experiences. Now this switch position over here would be 1.5 volts from there. The next switch position, let me clear this board again. The next switch position would be, 5 volts? Yes, it is 5 volts. The next position would be 15 volts. The next position would be 50 volts. And this position over here would be 150 volts. So now, as I turn my DC switch, then that voltage over here will be presented and passed up through. And if we had to do the calculation over here, you would see I would be presented 1.5 volts over there. And I would get my full meter deflection. I would use my multiplication scale to correctly read my 150 volts input. Alright. There's a funny thing that happens with this range selector over here, because this is the DC scale. But when we go above 150 volts, you can see down here and down here and down here, these switches only go across to this range selector B for DC. And then, but in any case, this range selector output, it comes to the same place. And then during DC, it's going to pass through, it's going to pass through the other way, out here. Back through there, off it goes, and it works just the same. So range selector A is only used for certain ranges of DC, and range selector B is used for all ranges of DC. Actually, range selector A is going to be used for certain ranges of AC, or not. It's going to be sort of, get a bit clever for certain ranges of AC, which we'll get to. But now, hopefully you see how DC is pre-scaled and then taken to the input of the differential amplifier for indication. So what's going on with this 1 meg resistor? As I said to you, this meter is an American meter. Inside of this meter, at this position, is a 1 meg resistor. Why? Well, let's go back to the European version of the Heathkit, or this Kyoritsu meter. You can see the Kyoritsu meter has a dedicated DC volts input, and the Heathkit IM11D for Deutschland also has this system. And it's because the probe, if I have a look at the probe, inside the body of the meter probe is a 1 meg resistor that then passes through there and goes that way. Whereas the American version, it doesn't have this extra AC, this extra DC input. It doesn't exist. So that when we are, it just is a sensing. So it's volts and ohms. This would over here would say volts and ohms input, and it's AC and DC and all things. And then the DC voltage would just pass through that 1 meg resistor. The 1 meg resistor is there because of capacitive properties of the leads. It's just to overcome those capacitive to pad those capacitive properties of the leads. And it's just the way that either the European version or the American version was built. Let's look at AC. If I put in 1.5 volts AC, nice sine wave coming in, AC volts comes through the function switch, gets selected, oops, not through there, it actually gets selected through here. It comes to one of 3.05 microfarad 3 kilovolt capacitors. There's one here, there's one there, there's one there. replace them. They are oil-filled capacitors and they get old and leak. So when you get an old VTVM, find all the capacitors and replace them. You'll be doing yourself a huge favor. It will calibrate correctly, it will last longer, it will behave like a meter should. Alright, so let's cut back to this now. The AC voltage has passed in through function switch B and it comes down and it now passes through that 0.05 3 kilovolt capacitor and comes to a range switch A again, but the second part of range switch A. And this over here, I call this the pre-scaling. Now if you are using voltages, and I can't remember how high they go, but in the lower voltage range, then what's going to happen is that AC voltage will pass directly through the second 0.05 capacitor and come and sit on the 6AL5, the plate on the one side and the cathode on the other side. This is going to now function as a full wave rectifier. Actually, it's a half wave rectifier. It's going to shunt negative it's going to shunt negative pulses to ground, or negative waves to ground, and it's going to amplify positive, not amplify but rectify positive. So over here we're going to, when we get an input, we're going to get a positive voltage sitting. Now that this AC waveform has been rectified into a positive voltage and smoothed by this 0.05 capacitor, that DC voltage is now going to pass through my prescaler, or not my prescaler, but my range select circuit, and depending on the range selected, either both switches are going to work or just the range switch B is going to work, and then pass on that voltage back out through my function selector switch to the meter. Now I've made a real mess over here, but you get the idea. For AC measurement, it gets prescaled, it gets rectified, and then it gets turned into a DC and switched back to the input of the meter. There's another problem that arises with this 6AL5 rectifier. When we switch on the meter, we end up with the heater element of the 6AL5 heating up these cathodes, and we get a cloud of electrons flying around inside of the tube willy-nilly. Let's say with zero input. I'm not talking about any input over here. These electrons, as they are flying around, will collide with the anode on the outlet on pin 7 and create a negative charge to come and sit over here. A very small negative voltage. Let's say it's minus 0.1 volts, minus 1 volt, something. But a very small negative voltage will naturally come and sit over here. This will then skew the multimeter readings. It will deflect the needle in a negative direction and it won't sit at zero. So we need to negate, we need to offset that bit of negative voltage when there's zero input. Let's say that it's minus 0.1 volts. If we don't want to put minus 0.1 volts over here, we're going to have to offset it. So we're going to have to put plus 0.1 volts over here. And the way that it's done is through this 88 mega ohm resistor, taking some of the voltage generated by the power supply through these resistors over here. I told you that we're getting about a 40 plus something, plus 40 plus 80, I can't remember, plus 80 volts. But we rectified and we pass it through this chain of resistors over here, and on this AC balance potentiometer, which is on the front of the unit, at least on the Kyoritsu, or on the Heathkit, it's not there, it's in the back. It has to be done during calibration. Alright. Anyway, we take some of that voltage, it's about 13 volts at this point from here, and we pass it through an 88 mega ohm resistor, and so that it gets radically dropped at this end over here, and we then can use that potentiometer to equalize this, or to offset this minus voltage, and set a proper 0 volts at this point with no input, with no AC input. and that takes care of that problem. Now any rectified AC voltage will be turned into a DC voltage, which will be passed through our range selector and through our function selector and go to the input of the meter driver. And that's AC voltage in a very nutty nutshell. Now we're going to have a look at ohms. In order to understand how the ohms reading works, I'm going to draw a little circuit. I'm going to have a voltage source. So over here I've got plus and minus volts. If I have a positive voltage going through two resistors and then connected to ground, let me call this resistance the known resistance RK and this resistance the unknown resistance RU. Okay? If I know what my voltage is known and this resistance is known, then as I pass current through the unknown resistance and the known resistance, if I have a look at the voltage drop across my known resistance, I will then get a representation of the unknown resistance. And that is the principle upon which this meter works, and I'll show you how it does it. In my AC ohms input, I'm going to make a resistor going to ground. Okay? And then down at the bottom over here, if I can find it, there it is a 1.5 volt battery, which is connected to ground on the one end, and the positive voltage passes through a set of resistors, known value resistors. So that is my set of known resistors RK, and depending on the ohms range that I select, the resistance is known, the voltage is known, and now I need to complete the circuit. So there's my RK, my known resistance, and my voltage that's known, VK, and now my current passes through the function selector switch and out through the AC ohms and through the terminal and through my resistor under test to ground, and I have a completed circuit. And now this section over here, you can see it's common at the switch, and this tab over here will short out the whole system so that I can take a measurement of the voltage at this point over here, bring it to the input of my meter driver and get a representative voltage. So now I've covered DC, AC and ohms readings. Calibration takes place with this function switch A, and in this position the function switch is only there to select in and out the different trim pots for DC positive calibration, DC negative calibration, and this is only found on the Kyoritsu. I find the Heathkits don't have that negative calibration. AC volts calibration, and yeah, that's it. Ohms adjust. Now the voltage calibration is always set for full scale deflection. So if you're going to calibrate, let's say for DC voltage, the best thing to do is select a range. Let's say you select the 5 volt range and then put a 5 volt DC in there so that you can take the meter to the full scale deflection. It's very important to calibrate at full scale deflection because these meters are designed to be accurate at full scale and then have 3% deviation from full scale at the rest of the range. Okay, that's the one thing. What other things did I miss? Yes, okay. These resistors here, coming back to this AC meter, these 3 resistors over here only come into play when we are dealing with the higher voltage ranges. And the reason for that is the voltage that I'm putting at this point over here is quite low, and at some point the cathode can become saturated. So as I'm starting to put very high voltages of AC into my diode, my rectifier, at some point it's no longer going to give me a linear output. So as I start to increase my AC voltage, my DC output will be fairly limited, but then as my cathode starts to saturate, I'm starting to lose linearity over here. So I can't use this portion of the diode. You understand what I'm doing? I like this linear portion so I can get a nice linear DC representation of the AC voltage coming in. So when the voltage gets too high, it gets pre-scaled through these resistors depending on the range that's being selected. So that'll be, for example, 1500 volts, 500 volts, and the pre-scaling will stop at 150 volts. To prevent this anode saturation and the loss of linearity at this point. What else is there to do? Yeah, the pilot light. Here's my 6.3 volt heater circuit. So 6.3 volts is providing heating power to the filaments, not to the filaments, to the filaments of the two tubes, and also to the pilot light. I normally replace the pilot lamp. If I see it's too dim, I replace it with an LED, and this is the LED circuit that I use. So I'm getting 6.3 volts coming in, and I take it through a diode to rectify it, and then through a resistor, and then through the LED to ground. And then just after the diode and across the resistor, I put a capacitor. I'll give you the values in a minute. So that's a 470 microfarad. 10 volt is enough. And this is a 150 ohms resistor with a white LED. And that gives me a nice bright light for my meter. Works great. What else? I've done the 1 meg resistor. Yes, I think I've done everything. So I hope that was useful, and I hope you've learned something by it. Please feel free to leave your comments or your questions in the comments box. Be nice, no need to be rude. And I try to answer all comments as well as I can. If you see something that I've said that was wrong, please let me know. Nobody's perfect, including me, especially me. And thanks for watching, and I'll see you again in the dungeon. Bye for now.